Good morning. Uh, Welcome wherever you are and whenever you may be. I want to thank you for tuning in to my presentation. Um, it's called Turning Up the Heat, using heat maps to visualize suspicious code to help students successfully complete programming problems faster. And that's a mouthful, and we'll try to get through it as quickly as we can. My name is Bob Edmondson, and along with my colleagues Steve and Edwards, I am on the faculty of the Department of Computer Science at Virginia Tech in Blacksburg, Virginia, in the United States. A lot of people ask me where Blacksburg is, and the pin marks the spot. We're in lovely Southwest Virginia. If you look at my background on my Zoom presentation, that's the view out one of the windows on campus. Um, so it's a wonderful place to have to quarantine. So time is short, and let's go ahead and jump right in. I can't go into a great deal of the background of our work, but I want to cover a few high-level concepts to give you some context. Um, Please review the paper for additional details for those of you who are interested. This work is based on applying spectrum-based fault location techniques to student programming exercises. We executed student submissions and applied instructor-provided reference tests to each. And then we used a tool called gzoltar to collect separate execution traces for each test, which positively or negatively weighed them depending on whether or not the code passed the test or not, and that line of code was involved in a test. And so once the suite of reference tests is complete, the execution traces are overlaid line by line, and with the result that each line receives a suspiciousness score, quote unquote, between 0 and 1. 0 meaning that that line was involved in every test it was part of and it passed, and 1 meaning that line was involved in every failed test that it was a part of. So 0 means that line always executed in tests that were successful, and 1 means that line executed in every test that failed. And so we get a continuum of scores between 0 and 1. And using those scores, we can then present them back to the student. The method we chose after a significant amount of research was to build a system that provided the feedback within context of the student's work product. So we created a visual tool that shows the results using a heat map style overlay on top of the student's source code. You can see an example of it here. Code that was more suspicious was on the red end of the spectrum, and code that was less suspicious was on the yellow end of the spectrum. So we used a spectrum between yellow and red, excuse me. And so we can adjust the hue values for those lines of code based on what the suspiciousness score was. And additionally, we provide a mouse over context so that the student can see the source file and the line and what the actual score was. So our research questions were, does the heat map feedback make it easier for students to improve their code? Are they able to use this to create submissions that are more correct submission over submission? And the second one is, does the heat map feedback allow students to complete their projects faster than students who don't have access to it? We wanted to see if students would achieve their maximum correctness score in less time with the heat maps than without. To test these, we looked at data from our automated grading system, WebCat, and we compared the performance of students from our fall 2015 CS1 course, where the heat maps were not available, to data from the classes from fall 2017 and spring 2019, where the heat map was offered in both of those courses. You can see the population sizes for each of these for students who consented to participate in the study. Um, Dr. Edwards was the instructor for all three of these terms, so we were able to control for instructor difference. We also examined the complexity of the assignments in each term to determine whether or not they were comparable. You can look at our methodology in the paper. In short, we determined that there was not a significant difference in the complexity of assigned projects. For example, Project 2 in fall 2015 had a similar complexity to Project 2 in fall 2017, as well as in spring 2019. So we were able to control for the differences in potential complexity of the projects because they weren't all the same. And to address the first question of the rapidity of code improvement, we determined the ratio of student submissions that increased the student's correctness score compared to the total number of submissions. And we calculated an average across the submissions for each term and compared them. And what we found, an increase in that ratio from fall 2015 to fall 2017 or to spring 2019 groups would suggest that heat maps played a role in promoting more frequent incremental improvements. And that's what we found. We grouped the assignments based on concepts covered. The blue bars show the spring 2015 results versus the green, which is fall 2017, spring 2019. And you can also see the dotted lines show the averages. And additionally, p-values are across the bottom. And in all cases, we saw a significant increase in the frequency of improvements. To answer the second question, we looked to see if we needed to define what completed faster meant. For us, that definition is achieving their maximum correctness score on a project in less overall project time. WebCat shows us when students submit, so we found the timestamps for the submission and determined what submission resulted in the maximum correctness score. And we divided that elapsed time by the total time for the first to last submission, and this gave us a ratio of the time to maximum score. The heat maps allowed students to achieve their maximum correctness scores faster. The average time to the maximum score should be reduced when the heat maps are available. And our data shows that in 3 of the 4 projects, that was the case. Heat maps we believe the heat maps allowed students to complete their projects faster in all cases except Project 2. And you can see that here, along with p-values across the bottom. So what do we find? For all 4 project sets, students were able to make more frequent incremental improvements, and in 3 of the 4 projects, they were able to reach their maximum correctness scores faster. And our belief is that the changes are tied to the way that the heat maps provide the feedback within the contents of the student's code. The heat map only highlights those bits of code that were involved in a failed test, and this focuses the student's attention towards code that could be defective. Students are also able to consider code that is somewhat suspicious versus code that is very suspicious. And so that can focus their efforts as well. We also think that the feedback may be preventing regression errors by focusing the attention of the student away from code that was not involved in failed cases. And because they're not injecting additional changes in that code, then they're not creating regressions. We did get some feedback from students that in some cases there was too much highlighted. They didn't know where to start. But we also believe this is self-correcting because the farther a student gets into the program or into the project, the number of lines that are going to be highlighted are going to necessarily be reduced. And so we think that the heat map may be more helpful the farther into the project they get. So if anyone has any additional questions or comments, here's my email. Please feel free to contact me. And again, thank you for your attention. I hope you're well wherever you are. And again, thank you for your attention. Cheers.